In this video, we're going to work a bunch of example problems related to the use of L'Hopital's rule for solving limits. And so in the previous video, we went through the textbook section, which was on indeterminate forms and L'Hopital's rule. And the main idea of this section was, it was more about indeterminate forms of limits and how do you solve those. And one of the main ways to solve those indeterminate forms is using L'Hopital's rule. But you don't always have to use L'Hopital's rule to solve an indeterminate form. And I gave some examples of this when we went through the textbook section, and we might see some examples here in this video. But all we're going to do here is we're going to work 10 example problems from this section of the textbook. So let's get started. What we want to do is find the limit, use L'Hopital's rule where appropriate. If there's a more elementary method, consider using it. If L'Hopital's rule doesn't apply, explain why. All right, so let's evaluate this limit here. And before, even before using L'Hopital's rule, we can consider, let's potentially factor this. So we have x, factor the numerator. So x and then 4, 2, minus 4 plus 2. Yeah, so there you go. So we get the limit as x approaches 4 of x plus 2. And now we could do a direct plug-in and we get 6. That's the limit. So we didn't even have to use L'Hopital's rule here. But we could have considered using L'Hopital's rule, because if we do a direct plug-in, or we take the limit as x approaches 4 of the numerator and denominator, we get this goes to 0 in the denominator, and then the numerator 16 minus 8 also goes to 0. And so that's indeterminate of the form 0 divided by 0, which we know we could have used L'Hopital's rule. So since it's an indeterminate form of type 0 over 0, we could have changed this. We could have said limit as x approaches 4, and then take the derivative of the numerator, 2x minus 2. Take the derivative of the denominator, 1. Okay, so this is equal to the limit as x approaches 4. We could factor out a 2. 4 minus 1 is 3. 3 times 2 is 6. So we could have done that. But we just used the elementary method. Why not? The idea is you use L'Hopital's rule if you're in a bind. But if you wanted to use L'Hopital's rule from the beginning, then that's fine too. All right, so here, we consider elementary methods, but I don't know how we could simplify this. I don't think we can. All right, so let's just do a direct plug-in. You start with a direct plug-in. If we do a direct plug-in and we get a finite number, then that's the limit. So e to the 2 times 0 is e to the 0. That's 1. 1 minus 1 is 0. Okay, so this goes to 0. And then sine of 0 is 0. So this is an indeterminate form of type 0 over 0. If you have an indeterminate form of a limit of type 0 over 0 or infinity over infinity, where the infinities can be or plus or minus infinity in the numerator, plus or minus infinity in the denominator, then you can apply L'Hopital's rule. It has to be one of those two types of indeterminate forms to apply L'Hopital's rule. Okay, we do have an indeterminate form of type 0 over 0, so let's use L'Hopital's rule. Because otherwise, how are we going to solve this? We could use, maybe a geometric argument, or we could, what we could do is we could plot e to the 2t minus 1, and then separately plot sine of t and see maybe this approaches 0 faster than this does. You could potentially do that. You could do like a direct plug-in, maybe, and plug in like 0.00001 and see to get an idea of it. But in general, we can't think of, I personally, I'm not a mathematician. I can't think of a way to solve this other than using L'Hopital's rule. So, all right, we can, because this is an indeterminate form of type 0 over 0, we can write this as the limit as t approaches 0 of the derivative of the numerator, which would be 2e to the 2t, divided by the derivative of the denominator. Okay, so now if we do a direct plug-in, cosine of 0 is 1. E to the 2 times 0 is e to the 0 is 1 times 2. This goes to 2, so this limit is 2. Okay, the limit as x approaches 0 from the right of natural log of x over x. Remember, when it comes to L'Hopital's rule, you can have x approaching, it could be anything. Infinity, minus infinity, one-sided limit, doesn't matter. Okay, so, but again, we might not even be dealing with L'Hopital's rule here. So let's see. So as x approaches 0 from the right of natural log of x, this is going to negative infinity. And then this is going to 0. Okay, well, minus infinity divided by 0, that's not indeterminate. Infinity divided by a tiny number is infinity. So this is going to be some form of infinity. We just need to analyze it to see is it positive or negative infinity. So this is negative infinity. Now, is this 0? Is this a very tiny positive number or a very tiny negative number? Well, we're approaching 0 from the right, so this is a tiny positive number. So this limit is a enormous negative number divided by tiny positive number is enormous negative number. All right, let's do a direct plug-in. So you have 0 in the denominator, and then 1 minus 1 minus 0, so 0 in the numerator. This is an indeterminate form of type 0 over 0. I don't see any way to solve this using a more elementary method. So let's try L'Hopital's rule. Derivative of the numerator is, derivative of the denominator. All right, so this is the same limit. We haven't changed the limit yet according to L'Hopital's rule. Okay, direct plug-in. E to the 0 is 1. 1 minus 1 is 0. 2 times 0 is 0. So again, we have another indeterminate form of type 0 over 0. We can use L'Hopital's rule again. Okay, so e to the x divided by 2. Right? Direct plug-in, e to the 0 is 1 divided by 2, so 1/2. This limit here, this limit is equal to 1/2. Okay, direct plug-in. 3 to the 0 is 1. 1 times 0, so this goes to 0. And then 3 to the 0 is 1. 1 minus 1 is 0. Okay, so we have an indeterminate form of type 0 divided by 0. So we can use L'Hopital's rule. Okay, so derivative of the numerator. Okay, we need to use the product rule. Derivative of the first is 1 times the second, plus derivative of the second would be 3 to the x natural log of 3 times the first. So, okay. All right, all over the derivative of the bottom, which would be 3 to the x natural log of 3. Okay, now do a direct plug-in. 3 to the 0 is 1, and then 0 times this, so x is 0, so this is going to be 0. So this entire numerator is going to go to 1. What about down here? 3 to the 0 is 1. So this is going to go to the natural log of 3. So this limit is going to go to 1 divided by the natural log of 3. Okay, so let's plug in x is equal to 1. You get 1 to some number minus 1. This goes to 0. Okay, b is not equal to 0, so you get 1 to some number that's not equal to 0 minus 1. This is also going to be 0. All right, so this is an indeterminate form of type 0 over 0. Let's use L'Hopital's rule. Okay, so ax to the a minus 1 over bx to the b minus 1. So in this case, if we plug in 1, you get 1 to some power. So 1 to any power is 1. A could be 0, but times a. So this is going to go to a. A could be 0. And then you plug in 1 here. You get 1 to some power. That's always going to be 1 times b. This is going to go to b. B can't be 0. So that's the limit. The reason why they're saying b can't be 0 is because we couldn't put a divided by b if b could potentially be 0. But since b can't be 0, then this limit goes to a over b. Okay, we plug in 0, we get this limit goes to 0, and then cosecant. So yeah, cosecant, the limit as x approaches 0 of cosecant is undefined. So, okay, let's do this. All right, we can write this as the limit as x approaches 0 of sine of 3x and then sine of 5x. Right? That's what cosecant of 3x is 1 over sine of 3x. Now we plug in 0, we get 0 divided by 0. So now we can apply L'Hopital's rule. All right, so derivative of the top is 5 cosine of 5x. Derivative of the bottom is 3 cosine of 3x. Okay, now you plug in 0. Cosine of 0 is 1. So this limit is 5 divided by 3. Okay, plug in 1 for x. You get 1 divided by 0, so this is going to infinity. And then natural log of 1 is 0, so you get 1 divided by 0, infinity. So infinity minus infinity. That's an indeterminate form. That's an indeterminate difference. Okay, so how do we deal with indeterminate differences? Well, the idea is we potentially want to put them in a form where it's one single quotient. Like use common denominators to combine the fractions. And from there, you potentially would get an indeterminate form of 0 over 0 or infinity over infinity, and you can use L'Hopital's rule. So let's do that. That's the general strategy. So, okay, we've got natural log of x times x minus 1 over x natural log of x, and then natural log of x times x minus 1, and then x minus 1, like that, okay? So, all right. Okay, so now let's plug in 1. You get 0 times 1, this goes to 0, minus 1 plus 1. So 0 minus 0, this goes to 0. What about here? Natural log of 1 is 0, 0 times 0. Okay, so 0 over 0. Now let's use L'Hopital's rule. Okay. Derivative of the top. What's the derivative of x natural log of x? Derivative of the first is 1 times the second, plus the derivative of the second is 1 over x times the first, so 1 minus 1, okay? And then, all right, now the derivative of the first, 1 over x, times the second is x minus 1, so x minus 1 over x, plus the derivative of the second times the first. Okay, so now we plug in 1. This goes to 0, plus 1 minus 1. So all of this goes to 0. Okay, the denominator, you get 1 minus 1, 0 over 1. This goes to 0, plus 0, so you get 0 over 0 again. All right, let's do this first. Let's multiply the numerator. Let's multiply this by 1 in the form of x over x. So you get x natural log of x over x minus 1 plus x natural log of x. Okay, so plugging in x equal to 1, you have 0 times 1, this goes to 0. 0 times 1, this goes to 0. So, okay, 0 over 0. Let's use L'Hopital's rule again. Limit as x approaches 1. Okay, derivative of the first times the second. plus derivative of the second times the first. Okay. Now the derivative of the bottom, 1 minus, or no, 1 plus, and then again, natural log of x plus 1. So we've got the limit as x approaches 1 of natural log of x plus 1 natural log of x plus 2. Plugging in 1, this goes to 0, this goes to 0, so 1/2. Okay, so we plug in 0 here, you get 0 to the 0 power. That's one of those indeterminate powers. How do you solve indeterminate powers? So it was 0 to the 0, infinity to the 0, or 1 to the infinity. Those are all indeterminate power forms. Okay, so you either write it as a function, write this as a function and take the natural logarithm of both sides. So you take the natural logarithm of this, or you write this as an exponential. So let's take the natural logarithm of this. So we'll say that y is equal to x to the natural log of x. Okay, so now we'll take the natural log of both sides. So natural log of y is equal to square root of x, natural log of x. Okay, so now let's take the limit as x approaches 0 from the right of this. Okay, so we get the limit as x approaches 0 from the right of the natural log of y is equal to the limit as x approaches 0 from the right of root x natural log of x. Okay. This goes to negative infinity. This goes to 0. So you have 0 times negative infinity. Indeterminate products. How do we solve indeterminate products? We rewrite the products in quotient form. So we pick one of these two. So we'll say 1 over. Okay, so if you plug in 0, you get negative infinity. And then here you get some form of infinity. So it's infinity over infinity. We can use L'Hopital's rule. Okay. So you get 1 over x, and then this is x to the minus 1/2. So minus 1/2 x to the minus 1/2 minus 1 is minus 3/2. Okay, so this is equal to the limit as x approaches 0 from the right, x to the first times x to the minus 3/2. It's minus 3/2 plus 1 is minus 1/2. So, okay, we've got, so minus 2, bring this 2 up, x to the minus 1/2, which is minus 2 root x, which is equal to 0. Okay, so what do we have now? We've got the limit as x approaches 0 from the right of the natural log of y is equal to 0. Okay, but we can raise both sides to the e power and write this as the limit as x approaches 0 from the right of e to the natural log of y is equal to e to the 0 is equal to 1. That's what we're looking for. We're trying to, we define this to be y. So this is the limit that we're looking for. So this limit is equal to 1. Okay, so plugging in 0, you get 1 to the, and then cotangent, let's see, cotangent. Well, all right, we know that cotangent is cosine of x over sine of x. So you have, as plugging in 0, you have 1 divided by 0. So this is you get 1 to the infinity. 1 to the infinity, that's an indeterminate form, an indeterminate power. All right, so let's write this as y is equal to 4x plus 1 cotangent of x. Take the natural log of this entire equation. Natural log of y is equal to cotangent of x, natural log of 4x plus 1. Okay, so now we could take the limit as x approaches 0 from the right of all of this. So what is the limit as x approaches 0 from the right of cotangent of x, natural log of 4x plus 1? Okay, natural log of 1 is 0, and then again cotangent of x goes to is an infinity. So infinity times 0, this is a indeterminate form of products, infinity times 0. How do we solve that? Well, we rewrite it. How do we solve this? Well, we bring one of these into the denominator. So let's bring cotangent into the denominator. How do you do that? Well, cotangent is 1 over tangent. Okay, so plugging in 0, tangent 0 is 0. Natural log of 1 is 0. So this is an indeterminate form of 0 of the form 0 over 0. So this is equal to, using L'Hopital's rule, 1 over 4x plus 1, and then times the derivative of 4x plus 1. So 4 over 4x plus 1. And the derivative of tangent x is secant squared of x. So secant of 0 is 1. Okay, so plugging in 0, this goes to 1, this goes to 4, so this derivative is 4. Okay, so that means that the limit as x approaches 0 from the right of natural log of y is equal to 4. Okay, but you raise both sides to the e power, and you get the limit as x approaches 0 from the right of the function is e to the 4. So that's the limit. Okay, and there you go. So there's some L'Hopital's rule example problems.